So this next section, I kind of combined a whole bunch of things. I wanted to just do an intro to limits section. I don't love the way the book organizes it, so this has little bits of section 2, 3, and 5. So let me just kind of sum up this paragraph that we've got right here. So this sort of thing that we did right here up in the previous section, we are starting to talk about limits, and it gives us a way to talk about what happens, like as the inputs approach a certain value, what are the outputs doing? As x gets closer and closer to some value, what is y doing? In the previous section, as h gets closer and closer to 0, what is the average velocity doing? And so it's not that we have a way to define exactly what's happening at that moment, but we can say what's happening as the input gets closer and closer and closer to a certain value. And so what we're introducing here is how at the end of the last section, we were able to kind of algebraically manipulate and figure out what was happening when h was 0. Sometimes we can do that, sometimes we can't. So the first method that I'd like to introduce is something called the table method. And so this first example right here, we've got this function, sine x over x. It cannot be algebraically manipulated the way the previous one was. As tempted as people are typically to try to cancel out the x's, that is absolutely not a real thing. So let's take a look at this. We're going to look at a table. So I will walk you through exactly how to do this, and I'm going to show you on the Inspire. So what we're going to want is a graph. So if you either open up a new document or add a page, so hit Control and then this document button, and you can add a new page. And what we want is a graph page. Okay, so add graphs. If you were working on an 83 or an 84, you will just hit y equals, which is kind of in the upper left-hand corner around here, and type in this function. So we are going to put sine x in parentheses. On the Inspire, there is a trig button right next to the 7. Select sine, put your x in there, and then you close parentheses for the x, and then close parentheses for the numerator, and then divide by x. Okay, so two things. First of all, hit enter. Let's just see where your graph falls. Okay, so this is what your graph may look like. The next thing I want you to check, so see this little touchpad in the middle, can move this cursor. I want you to move the cursor up to the corner where the battery is. See how mine says RAD? That stands for radian. That's the mode you want to be in. If it says DEG, that means you're in degrees. So here's what you do. You just click right in the center there. You're going to go to Document Settings, which is the second option. And then you just arrow down. Oh, mine says it's on degree for some reason now. You want to make sure it's changed to radian, and you might as well just go ahead and make that a default setting for your calculator. So just either use your cursor right here, click on Make Defaults, and yes, you do want to make that your default setting. We only work in radians in calculus, so there's no point in your calculator ever being in degrees. Okay, so mine was in radians before, so that's what it already looked like. Yours may look different. So that's the graph. We want to see what's happening as sine x over x approaches 0. So first thing I will note, if you try to plug in 0 into this function right here, sine of 0 is 0. And of course, if you plug in 0, you get 0. So you'd be getting 0 over 0, which is not a number. We call that an indeterminate form. So when you look on the graph, if you look right around here, it actually looks like it hits 1. So that's what it looks like when we talk about investigating graphically. If you're just looking at it, it looks like it's going to hit 1. Okay, so we are going to write f of x and then throw in, let's see, as x approaches 0. Okay, so f of x appears to approach 1 as x approaches 0. Okay, so now this we are going to investigate numerically, which means by making a table. So if you are on the Inspire, we've got a couple steps that we need to take here. First, you are going to hit the Control button and then the letter T. That is a shortcut that opens up a table. So you're looking at this table, and we've got tenths over here, and then just single values like 1, 2, 3, 4 over here. So it doesn't really match up with what we want, but there's a way to change your calculator so that you can input any x value that you want. So from the table, so make sure that you've got something highlighted over here because it's got separate menu options for the graph side versus the table side. So like I said, make sure something is bolded over here. So when you hit menu, And then it's got all these table options, so go down for the table options, and then you're going to edit the table settings. And so all we're going to do is just arrow down, and then the independent variable, that's the x, you're going to change that to ask, which basically means that you can put in any value that you want. If you're on an 83 or if you're on an 84, what you're going to do is you've got these table settings, like you'll have 5 buttons up along here, and you're going to go into the second, I think you're going to hit second and then the table, and it'll have your table settings up there, and you can do the same thing. You can just go and change the independent variable to ask. Okay, so and then if you're on the 83 or 84, then you'll have to go into the table, and then it should be blank, and you can add in whatever you want. So notice ours is blank, so we're just going to input the x values that we want. So -0.3, hit enter. I'm just going to input them all right now, and then I'll write them. And then -0.1, so let's get a few of these. So I'm going to write at least as many digits as I can see here. So 0.98506, or if you go an arrow over, see how it shows really teeny, teeny, tiny what all of those digits are. So 0.98506. And then at -0.2, we have 0.99334. And then at -0.1, we have 0.99833. So let's keep inputting values here. So back over to the x column, we're going to type in 0. And it says the number is undefined, which we knew that. And then 0.1, 0.2, and 0.3. So like I said, I'm going to input them all now, and then I'll write them down. So notice these 3 values here are the exact same as these 3 values. So it's a perfectly symmetric function around the y-axis. So if you plug in a negative x value or that same positive x value, you'll get the same thing. That's what gives it that symmetry. So this for 0, it is undefined. And then it repeats the values back. So it's completely symmetric. Okay, so what we're trying to come up with is what's happening as x approaches 0. So you can come in this way, x is getting closer and closer and closer to 0, or you can come in from the right, and x is getting closer and closer to 0. What you'll notice is that as you come in from the left, these values are getting closer and closer to 1. And as you come in from the right, these values are getting closer and closer to 1. So as x is approaching 0, the table also tells you that y is approaching 1. Okay, so what the graph looks like is it's got something like this. Kind of looks like a sine curve. It kind of wiggles around over here and has this little bit, kind of goes up. Instead of actually hitting 1, if you were able to zoom in far enough, you would actually just see a hole there. And it comes back down, so a little something like this, and then it keeps wiggling off to both sides. So something like that. So when you try to plug in x equals 0, it's actually undefined, which leads to the appearance of the teeniest, teeniest little hole. Okay, so let's write down some notation. So our limit notation looks like this. We write limit, and then you write x approaches c underneath, and then you write whatever the function is, and then equals whatever the limit is. So you write it like this. The limit of f of x, so whatever the function is, like in the previous problem we would say the limit of sine x over x, as x approaches c, is L, and then whatever that limit is. So this is the sentence that I need you to know. I need you to speak about limits in the right way. I need you to use the correct notation, correct terminology, and everything. Okay, so in example 1, what we saw is that the limit of sine x over x as x approaches 0 is 1. Okay, so that's how you'd read that. This is our function, this is whatever x value you're approaching, and then this is the limit. That's what the y values get closer and closer to as x gets closer and closer to 0. Okay? So this sentence, super, super, super important sentence here. The existence of a limit does not depend on whether the function is defined there. Okay, so like here, our function is not defined there. The function might be defined, it might not be defined. The existence of a limit does not depend on whether or not the function is defined at that value. So we've got 3 different examples, very, very, very similar. We're going to take a look at all 3 of these. So this function right here, We've got a numerator of x squared minus 1 and then a denominator of x minus 1. What happens with that is that you get a function that looks something like this. So watch what happens with this numerator. Numerator factors, very easy factoring. So what happens is that this function behaves exactly like this function, except if you tried to plug in 1. If you tried to plug in 1, you'd get 0 over 0. That would be undefined. So I think you guys have probably seen functions like this before. It looks just like this line, except there's a hole if you try to plug in x equals 1. So it looks something like this. Okay, so there's our y-intercept is at 1, and then it's got a slope of 1. But if I try to plug in positive 1, there ends up being a hole here. Okay, so it's going to look like that. Looks just like this line, slope of 1, y-intercept of positive 1, but if you try to plug in 1, there's a hole there. You could plug this into your calculator, you would see something very similar. Okay, we're going to draw these all first, and then we'll talk about the limits. Then our next function, g of x, looks just like this. The first part looks just like this function we just drew. For everything but 1, we're going to draw this. And so it actually looks just like this as well. So let's start there. So for everything but 1, so that means it's still going to have a hole right here, still going to have a y-intercept right here. Okay, so this is the first piece of the piecewise defies function. And then when x is 1, y is 1. So then you've got another point right here. Okay, so since the point was not defined here, they redefined it somewhere else. And then finally, just a nice simple line, x plus 1. So slope of 1, y-intercept of 1. It's going to look something like this. Looks just like the other two, except it doesn't have a hole. It's a much simpler version. Okay, so we want to use this example to kind of really prove a point. So this one right here, we would say the limit of our function f of x as x approaches 1. That's what we're trying to figure out. So as x gets closer and closer to 1, so x is 1 is right here. As I get closer and closer to that x value, what is my y value approaching? As I get closer and closer to that x value, what is my y value approaching? And remember, it does not matter what happens at that point. We don't care that there's a hole there. We just want to figure out what it seems like the y value is going to do. So as x gets closer and closer to 1, y is getting closer and closer to 2. Okay, so we say the limit is 2. Next one, limit of this next function, g of x, as x approaches 1. So as x gets closer and closer and closer to 1, what is y getting closer and closer to? Well, it's getting closer and closer to the number 2. We do not care that all of a sudden it jumps, because we don't care what happens at x equals 1. We care what happens as we're getting closer and closer and closer to 1. And from what we can tell, as we're getting closer and closer and closer to 1, it looks like y is getting closer and closer and closer to 2. And then h of x is actually a pretty straightforward example. We're saying what's happening as x approaches 1? Well, as x approaches 1, y goes right to 2. There's no hole, there's no jump, there's nothing fancy at all. It looks like it's going to hit 2, and it does in fact hit 2. So we say that the limit is 2. So even though we've got 3 different scenarios here, all of their limits are the same because it doesn't matter what happens right at that point. Okay, so we've got a couple of things that we can start talking about in terms of basic facts of limits. So here are 2 really easy ones. The limit of k. So k is a constant. So say you've got just like a normal horizontal line. If you're looking at a horizontal line, as x approaches c, well, guess what? It's just going to be that horizontal line. So say you have something like this. If you have a horizontal line, no matter what x is approaching, the y value is always the same. Okay, so the limit of a horizontal line is always just whatever that value is. That's one fact that we can use. It's always going to be true. And then the second one is the limit of x. So x is this very simple linear function, goes through the origin, has a slope of 1. The line y equals x means whatever the x value is, that's the y value. So as x approaches some value c, y will also be c. This has the point 0, 0, 1, 1, 2, 2, -1, -1. So as x approaches a value, y approaches that very same value. So these are two very easy limit rules that we can use and kind of expand upon. Okay, so using these two, we're going to come up with some different properties. All right, so let's get just a few properties here. Okay, so properties of limits. We will start here. So first property says if you add two functions together. Okay, if you add two different functions together, all you have to do is add their limits together. The limit of f of x is L, and then the limit of g of x is m. So if you add two functions together, you just add their limits. Very similar for subtraction. If you subtract one function from another, property of limit says you just need to subtract one limit from the other. Multiplication works like this too. So if you've got a function f of x times a function g of x, you would just multiply their limits together and you would just have L times m. This one's a little bit different. Let's say you have some sort of constant multiplier. Like let's say you have a number k and you're multiplying it by a function f of x. All you would have to do is multiply the limit by that same constant. Okay, and then our fourth operation is division. We haven't seen that yet. If we divide one function by the other, as I'm sure you can expect, all we have to do is divide the limits by each other as long as m isn't 0, because you know you can't divide by 0. And then the last one, if you've got some function and then it's raised to a power. Okay, so let's use j as a power. So all you have to do is take L and then raise it to j. Okay, as long as that comes out to be real. Like if L is negative and you're trying to take a square root, that won't work. Okay, so those are some properties. We are going to do just a couple quick examples using those properties. Okay? So this right here, we start off with the addition and subtraction properties. So if we're trying to find the limit of this whole polynomial, what we can do is we can take the limit of this, add it to the limit of this, subtract it, or subtract from it the limit of this. So that's using properties 1 and 2. So let's start there. Okay, so I'm using, like I said, both properties 1 and 2 right now. Okay, so this one. This follows property 6. If I have a power on the outside, I just take the limit and then raise it to that power. It's the limit of the function and then raise the whole thing to that power. Plus, here I have property 4 and property 6 going on. I can move the constant to the outside, and then I can raise to a power. Now this one actually goes with something I wrote down on the previous page. Since this is just a constant, I just use that value. If my function is just 3, that means y is always 3. So this is just going to be 3. Okay, and then see what I have in parentheses here? If I just use the function x, as x approaches c, y approaches c. So this is just c, and then I have that third power on the outside, plus 4, and then this is just a c to the second power, and then minus 3. Okay, so if you look what happened here, look at this function, compare it to this function. There's no difference between this function and this function, except for the fact that I replaced the x's with c's. That is called direct substitution. Okay, so that is my first and easiest method of limits. I did all these fancy, crazy properties just to basically end up plugging the c in. So if you can, just plug in the value. If it doesn't work, then you might have to do something more complicated. If it doesn't work, that means there might be a hole, or we'll talk about asymptotes, things like that. So if we look at this one right here, I could do all these crazy properties. I could do property 5, where I split it up into numerator and denominator. Then I could do properties 1 and 2, where I split up the subtraction, and then do property 6 with the powers. But I know that all that's going to happen is I'm going to directly substitute. So this just ends up being c to the fourth plus c to the second minus 1 over c to the second plus 5. I plug directly into my function. And then depending on what c is, maybe it might not end up working. This denominator could never be 0 because it's c squared plus 5. I could never make that equal 0. But it is possible. The point here is that my first goal is to go for direct substitution. Okay, so we're going to cut the lesson in half, so that is the end for right now.